Hello everyone, and welcome back to another tutorial video. In this video, what I will be going over is problems, such as some of the ones that you have assigned on your homework 4, that involve the logistic equation. These are problems mostly from section 2.1. Now, as a quick reminder, I have already written up here on the screen both the format of the logistic equation, which always shows up in the form dp dt, where of course p is population, t is time, is equal to k times p times m minus p. Keep in mind here that both k and m must be constants. And of course we're going to have, say, an initial condition, p of 0 is equal to p naught. Alright, in the very first problem in your homework set, I actually asked you guys to show that given this kind of logistic equation, the solution is going to always follow the form p of t is equal to m times p naught divided by p naught plus parens m minus p naught close parens e to the negative kmt. That's the first problem on your homework set, and you should be able to figure that one out just using tools from the previous chapter that we went over and stuff that was covered on exam 1. So for the rest of this video, I'm going to assume that we know this and that this is all established, and I'm probably going to leave this up somewhere up in the corner of the screen to refer back to as necessary. There we go. Alright, now with that established, I've now written up the problem, the exercise, that I want to go over in this video. The exercise is as follows. This is exercise 2.1.17, taken from section 2.1, of course, in your textbook. And I believe problem number 3 from homework 4 follows roughly this format. The problem is as follows. Consider a rabbit population, p of t, satisfying the logistic equation dp dt equals a times p minus b times p squared, where b, or capital B, is equal to AP is the time rate at which birds occur, and capital D is equal to lowercase b times p squared is the rate at which deaths occur. Now, if the initial population is p of 0 equals 240 rabbits, and there are 9 birds and 12 deaths per month occurring at time t equals 0, how many months does it take for p of t to reach 105% of the limiting population m? Alright, this is a pretty lengthy word problem, but what's actually being asked is pretty straightforward. We have a population of rabbits which follows the logistic equation, and you can see that at initial time, our death rate is greater than our birth rate, which means that this population is higher than what is called the limiting population of the logistic equation. That means that this population is gradually going to go down and decrease to approach that limiting value m. Now you are being asked to find how long does it take for it to get within 5% of that limiting population. Now there's a couple of steps that are going to be required to solve this problem. And the steps, not necessarily in order, are roughly going to be as follows. First off, you need to identify what the value of m is. Note that here we are given the logistic equation dp dt is equal to ap minus bp squared. That's a slightly different format than what you see up in the top left corner, which is kp times m minus p. So we're going to have to rewrite that to follow the format that we're familiar with and that I've written in the top left corner of the screen. Once we've done that, we'll be able to do two things. We'll be able to first find the population m, and second, find the solution, which is going to follow the format that I've written up above. So let's write these steps out. So step 1. So step 1 is going to be to rewrite the equation in the form p of t, or dp dt rather, is equal to kp times m minus p. Now to do this, we'll need to use the info given to find the values of lowercase a and of lowercase b. All right, that's going to be our step 1. Let's see if I can move this over here. There we go. All right, once we've done that, step 2. Step 2 is very straightforward. We're going to identify k and m. Also, compute, in this case, 105% of m, since we're going to need that later. Let's see, let's put this over here. And last but not least, step 3. Solve for p of t using the known formula. That's the one I've written in the top left corner of the screen here. And then set p of t equal to 105% of m, and solve for t. All right, that's all that's going to be required for a problem such as this one. Just follow these 3 steps. Hopefully it seems at least somewhat sensible what the plan of attack is here. Luckily, as I've mentioned, the solution of the logistic equation is already known to us. So we are not going to need to go back over the process of, trying to solve the differential equation and such. We simply need to set it up properly, identify what the parameters k and m are, and then use that to get the solution and plug in and find the value of t that we're looking for. All right, I've made a little bit of space on this screen, so let's get started with step number 1. And step number 1 is, of course, the rewriting step. So first, we'll need to find lowercase a and lowercase b. And we're going to do so in the following manner. So we have the following. We have that a times p is equal to capital B, the rate at which births occur. And we have that lowercase b times p squared is equal to capital D, the rate at which deaths occur. We also know that at time t equals 0, there are 9 births and 12 deaths per month. And we also know that at that time, our population is equal to p0 is equal to 240. So at time t equals 0, we know that b is equal to ap is equal to 9. We have capital D is equal to lowercase b times p squared is equal to 12. And p is equal to p0 is equal to 240. This allows us to solve for lowercase a and lowercase b. So this gives that a times p0 is equal to 9. In other words, a times 240 is equal to 9. So in other words, we have that a is equal to 9 over 240. Getting small numbers like these is expected. Don't freak out if you see some pretty small numbers. You're still doing fine. Now we also have that b times p0 squared is equal to 12. So this means that b times 240 squared is equal to 12, which means that b is equal to 12 over 240 squared, which is roughly equal to 1 over, should be what, 240 times 20? Now I should note, just for simplicity, that if we reduce both of these fractions, we get that a is going to be equal to 3 over 80, and b is going to be equal to 1 over 4800. So next up, we plug these values back into our equation. So this gives us that dp dt is equal to, we have a times p. A is 3 over 80 times p, minus lowercase b times p squared, and b is 1 over 4800 times p squared. And now what we are going to try to do is to, well, first put under common denominator, and then factor. So common denominator gives us that dp dt is equal to, I believe this gives us 180 over 4800 times p, minus 1 over 4800 times p squared. And then factoring this gives us dp dt to be equal to 1 over 4800 times p times 180 minus p. All right, at this point we have completed that very first step that we wanted. We have written that differential equation in the format k times p times m minus p. And all we had to do that, again, is just to first off put under common denominator the two values of lowercase a and lowercase b, and then we simply factored it out as much as we could. And this gives us our little value in front here. Let's go in red pencil. This value here is going to be equal to our k, and this value here is going to be equal to our m. Now on the homework, on problem I believe number 3 that I signed on the homework, you will have a problem I think very similar to this one, except the numbers might be a little bit different. However, once you get to this step, you should still have something that looks similar to this, and those are the terms that you're going to identify as k and m. Speaking of which, that's going to be step number 2, so let's move on to that. All right, we now have step 2, which is identify k, m, and calculate 105% of m. And this step is fairly straightforward. Since dp dt is equal to 1 over 4800 times p times parens 180 minus p, we see very simply that k is equal to 1 over 4800. Again, don't be too worried if you have something along the lines of this, some very small number or some weird looking fraction. That's totally normal in problems like these. And m is simply going to be equal to 180. Now we can see 105% of 180 is equal to 189. So that's the population that we're going to be interested in looking at in this problem. Now, before I move on to step 3, just to keep things color-coded like I like to do, I'm going to surround K with red pencil, and M is going to be in yellow pencil. This is going to come in handy once we're plugging in values. Alright, with all that done, let's move on to the final step, step 3. Step 3 is just to solve and plug. We know that the solution is P of t is equal to M times P naught over P naught plus M minus P naught e to the negative kmt. And as I like to do, and you don't have to do this necessarily, but I think for videos like this it helps keep straight what is what, I'm going to go over and color code the terms that we need to plug in. You can see that k only shows up once in this formula, whereas m shows up a couple of times here, here, and of course here. Last but not least, keep in mind that we also have P0 that we need to plug in, and P0 of course is equal to 240. Alright, time to plug all these values in, see what we get. So we're going to have, in the numerator, m is equal to 180. That's being multiplied by P0, which is equal to 240. That's a times. Now, in the denominator, we have P0, that's 240, plus m is 180, minus P0, that's 240 again, times e to the negative k is 1 over 4800, times m, which is 180, times t. Alright, I'm going to simplify this a little bit before proceeding any further. You'll note that that 180 minus 240 is going to be equal to negative 60. And we can actually cancel out a 60 out of the numerator and the denominator. So simplifying this gives us 180 is 3 times 60, so that's 3 times 240. Divided by 240 is 4 times 60. So that's 4 minus 1 times e to the negative, and that's going to be, I think, 3 over 80 times t. This, of course, is our P of t. Alright, of course, this can be simplified maybe a little bit further, but there's no real need to do that at this point. So next, plug in. We're going to plug in P of t is equal to 189. And then we're going to solve for t. Alright, so let's do that and let's finish up this problem. We get the following. We're going to get 189 is equal to 3 times 240 divided by 4 minus e to the negative 3 over 80 times t. Now, if we cross multiply, we get that 189 times 4 minus e to the negative 3 over 80t is equal to 3 times 240. Now, if we actually divide both sides by 9, we're going to get this is 21 times 4 minus e to the negative 3 over 80. This is dividing by 9. Times t is equal to 80. Now this, of course, gives that 4 minus e to the negative 3 over 80 t is equal to 80 over 21. Now this in turn, of course, gives that 4 minus 80 over 21 is equal to e to the negative 3 over 80 t. Now we take natural logs of both sides to get that negative 3 over 80 t is equal to natural log of 4 minus 80 over 21. And finally, this gives us that t is equal to natural log of 4 minus 80 over 21 divided by negative 3 over 80. Alright, now at this point we are basically done. But I still have a couple comments I want to make. First off, please note that at this point so far, I have made a very conscious decision to not round until this final value. So if you actually plug this value in, you'll see that this gives you approximately, and please be sure when you approximate, I actually docked a number of you guys a point or so on the exam for using an equal sign when you are approximating. There are pretty important reasons why you're not allowed to do that, and the long story short is that if you were allowed to put an equal sign between things that were only roughly equal to each other, all of math would break and we wouldn't be able to do anything. So I think that was worth docking at least a point, but in general, if you're approximating or rounding values, you can just use the approximately equal sign, and there's no worry at all. In this case, this gives us approximately 44.22 months. And first note that you can double check this by plugging it in. Into this equation up here. So say you're on an exam. Of course, we don't have any exams in class, but if you want to double check that you didn't make any mistakes, you can always plug it back into the solution equation for PFT, and you should get something that comes out pretty close to 189. I plugged this into my computer, and I got 188.99979, so pretty close. Now the other thing I want to point out, and this is very important, is do not round prior to this final step. And this is very important. First off, just on the homework set, if you start rounding a little bit earlier, say you start rounding, a couple lines before or something like that. You approximate that 80 over 21, or approximate round that natural log of 4 minus 80 or 21, or something of that sort. And you try to plug that value into the computer system for the homework. It's probable that you'll be off by a decimal or two. And if you're off by just a little bit, the computer is going to mark you as wrong, even though your work most likely was pretty much correct until then. So just from a practical perspective, not rounding until the very end means that you probably won't get marked wrong unnecessarily by the computer system. Now, from an actual mathematical perspective, There is also a reason why we try not to round too much prior to the final steps if we can avoid it, because those rounding errors over the course of a problem like this can really compound on one another, and in certain scenarios, maybe not this one necessarily, but there are a number of scenarios in real life where if you start rounding too often in intermediate steps, your final solution will be off by quite a bit more than you might expect. So don't let those rounding errors have a butterfly effect on your answer. Don't let this, go to waste and cause the computer system to mark you wrong. Try not to round until the final step. Alright, aside from that, that's pretty much all I have to say about this example problem. Hopefully this is a helpful tutorial on how to solve this. There will be a couple other tutorial videos that I'm going to make, well, at least one other tutorial video I'm going to make for homework set number 4. But as usual, let me know if you have any questions remaining or need any other assistance, and I'll see you guys again in class and in another video. Bye-bye.